Good afternoon, everybody. My name is Estavayer-le-Lac Monte from the Italian National Institute for Astrophysics in Rome. And in my presentation, I will discuss how to use CubeSats to map the radiation environment in equatorial low Earth orbits. This is my outline, so I will tell you briefly why it is important to study the particle environment related to satellites, and in addition, why the equatorial low Earth orbit is important for satellites and especially for scientific research. I have not time, of course, to go into details, but I will briefly give some hints on why there are some large uncertainties in the particle models of this particular orbit. And this is an important opportunity for CubeSats, since there are light and low demanding particle monitors available now. After this, I will discuss some trade-off for CubeSats mission, in particular satellite orbit and stabilization and the type of the transceiver and of the ground station in order to accomplish this task. And in the end, I will discuss a possible configuration of a CubeSat-based mission to map the particle environment in this type of orbits. So why we are interested in charged particles in orbit? Basically, when they interact into satellite instrumentation, they can affect the functionality and the performance, for example, for solid-state devices, and we may have two, broadly speaking, type of effects. The first one is the integrated effect of many interactions, and this is generally under the name of total ionizing dose or non-ionizing energy losses. And in addition, we may have single event effect, that is, effects which are produced by the single interaction of a particle. And in particular, we may have latch-up in ASICs or single event effects, a single event upset, in memories. In addition to that, particles interacting in instrumentation may, for example, increase the background of scientific instruments. This is, for example, the case of high-Z scintillators for hard X-rays. It is the phenomenon which is commonly known as phosphorescence. Or, for example, charged particles represent the background in tracking detectors for gamma rays. Why we are interested in low Earth orbit? So just a few words of definition. Low Earth orbit is generally considered with an altitude between about 160 kilometers and 2,000 kilometers. These orbits are practically below the Van Allen belts. This means that satellites flying there will experience a reduced flux of charged particles. In addition, if we take into account low Earth orbits near the equator, so at low inclination, the passage through the South Atlantic anomaly are really brief, 10 to 12 minutes, for example. So we have not only a small flux of particles, but also a small variation around the orbit of the particle flux, which produces a small background modulation. For these reasons, these type of orbits are suitable for missions in high-energy astrophysics, where the particle flux is important. Some representative examples of satellites in low Earth orbits are the International Space Station, or most of the satellites in gamma and ray astrophysics, just to name some, the Compton Gamma Ray Observatory, or the Italian and Netherlands BeppoSAX, or satellites for gamma rays like Agile and Fermi, or for X-rays like Swift and NuSTAR. Other example is, of course, the Hubble Space Telescope. This is what I said before is summarized in these figures. So the dashed light blue curve represents the maximum altitude of Leo, which is compared with the omnidirectional flux on top left and electron flux on top right. So you can see from these diagrams that these orbits are really at the bottom edge of the particle belts. In addition, the distribution of these particles in geographical coordinates is given in the bottom left, where you can see the famously known South Atlantic anomaly, which is centered broadly on South America. During the years, with many observations on satellites, models for the so-called trapped particles, which are the particles that I'm referring to. So models for these particles have been built. And in order to describe the flux at different latitude, longitude, and altitude. And these are, for example, the AP8E8 and the new AP9 E9, or some other examples. The equatorial low Earth orbit, which I have shown you before, is important for scientific research, is not well sampled by these models. And this is because in these orbits, the particle flux has some rapid variations with both altitude and inclination. So these large flux variations, while introduced in the models, gives some very important variation of the predicted flux from the model with the orbital parameters. In addition, we have a soft proton component, which is described in papers by Petrov and collaborator, which is not yet included in the models, and an east-west anisotrope in the flux, which is measured, and which has a ratio of about 4 to 5 for protons above 50 MeV at 500 kilometers, which is referred to in these reference. This is an important opportunity for CubeSats. Why? Because there's a trend in the development of particle monitors toward the reduction of size, weight, and power consumption. We are now in a situation in which such miniaturized particle monitors can be installed above CubeSats. And this type of CubeSats can be used to measure the particle environment, especially in the equatorial low Earth orbits I was referred to previously. And they may be used to map this environment before launching satellites for scientific research, and so they may use to help the design of larger and more expensive missions. Given the low amount of resources which are needed by CubeSats, this approach can be applied to many different orbits of interest. Here in this table I summarized the characteristics of some of these particle detectors that I have found in order to show this trend toward miniaturization. We can start with the Standard Radiation Environment Monitor, which is a project by ESA and Switzerland, mainly PSI and Contraves, which is flying aboard satellites like Integral, Herschel, Planck, Proba-1, and others. This has a mass of about 2.5 kilos and is sensitive in the energy band between 10 and 400 MeV for protons, half an MeV up to above 10 MeV for electrons. The next generation radiation monitor is the evolution of the previous one. In this case, this is also an ESA project in which there's a contribution by Switzerland, Norway, and France. You can see from the table we have a reduction in mass power consumption and also in the energy threshold for both protons and electrons. And then there's the so-called highly miniaturized radiation monitor, which is a project by ESA and UK. In this case, we have an instrument with 52 grams, about 1 watt of power consumption, and energy thresholds of the order of 1 MeV for protons and 0.06 MeV for electrons. There's also an American monitor, which was presented a couple of presentations before mine, which is called Reptile, which has a mass comparable with the NGRM and similar thresholds for protons and electrons. So here I will discuss some trade-off for CubeSats in order to build a mission to map the particle environments of the Earth. So, since due to the shape of the South Atlantic anomaly, the flux rapidly changes with the altitude, we want to measure the flux between, say, 500 kilometers and 600 kilometers, which are basically the altitudes at which the satellites for science will fly. And we can propose two options for this task. We may use two CubeSats with the same inclination and different altitude, or we may change the altitude of a single CubeSat. And this can be achieved using a deorbit system like a tape. Of course, we prefer an equatorial orbit, but a sun-synchronous orbit, which is more common, can be used as an option. So I'm sorry, I have to hurry up because my time is running up. This is the example of how we can use the tape, the orbit tape, in order to reduce the satellite orbit. The altitude control will be simple because we need a zenith pointing, and this can be accomplished using a gravity gradient stabilization. We can put one of these monitors in the zenith direction and the other one at 90 degrees. By spinning the satellite, we can map the east-west anisotropy of particles. Of course, we are basing on the fact that near the equator, the pitch angle is around 90 degrees, so they will come in interaction approximately from the zenith. Referring to the transceiver and the ground stations, we can use a VHF network of about 12 stations near the equator. They have been used for the HETI-2 NASA satellite for gamma ray burst observation. And our requirements on the ground transmission rate are compliant with this type of network. Also, the satellite control could be operated by this network using UHF transmitter. So, just to summarize the possible configuration, we can use a single CubeSat 2U or 3U launched at 600 kilometers on equatorial orbit, or sun-synchronous if this is an option viable in case of only this one can be available, with zenith pointing by gravity gradient stabilization and spinning. Of course, the HMRM particle monitor, which is very light and low consuming, is a good opportunity for us. We may put one in zenith direction and the other one at 90 degrees. We can use the tape in order to decrease the altitude and also to deorbit the satellite at the end of life. And this UHF VHF transceiver and network for downlink and control, and finally a GPS module to measure the position and velocity of the satellite. I can leave you here the conclusions which summarize what I have just said. Thank you.
I have one quick question. We have a question up there? Okay, you summarized very well then. Thank you very much.